Hi everyone, this is lecture 11th of data science series, and today our topic is understanding logistic and Poisson's regression. So, have you ever Hi everyone, this is lecture 11th of our data science series, and today I'm going to discuss about the topic logistic regression and Poisson's regression. So let's get started. So guys, have you ever wondered how to predict outcomes like whether the customer will churn or how many products they'll buy? So these two models are your go-to tools. We'll break down their fundamentals, interpret their outputs, and discuss where to apply them in real life. So let's get started. Now, fundamentals of logistic regression. Logistic regression firstly is widely used for predicting binary outcomes, that is, situation results in either yes or no, true or false, or simply 0 or 1. So, key concepts in logistic regression. So, firstly, we have binary outcome, that is, logistic regression predicts the probability of an event occurring. For example, will a customer make a purchase, that is yes 1 and no, that is 0. Second, is the tumor malignant, that is yes or no, that is 1 or 0. So, these was about binary outcomes. Now, for predictor variables, that is, these are the independent variables that explain the variation in your outcome. For instance, customer age, income, or shopping frequency can help to predict whether they'll make a purchase or not. Then we have logic transformation, that is, logistic regression model uses a logic transformation to convert probabilities into a linear function that makes easier to the model to implement. And lastly, we have odds ratio, that is, odds of an event are the ratio of its probability occurring. That is, consider odds is equals to p by 1 minus p, that is probability minus 1 minus p, that is not occurring. And the odds ratio tells us how much the odds change with the unit increase in the predictor variance. Now, logistic function and probability mapping. So, at the heart of logistic regression lies with the logistic function which maps the predicted values to the probabilities. That is, the result S-shaped curve can ensure all the probabilities that falls between 0 and 1. For example, if incomes increases, the probability of making purchase rises, but it plateaus at 1, meaning that it can't extend 100%. And this is our as logic curve, and then we have probability range and then mapping values. Now, model interpretation performance. So we have coefficient interpretation, that is, the coefficient in regression represents the change in the log odds of the outcome for a unit change to the predictor. For example, in positive coefficient for an income suggests higher income increase and the likelihood of purchasing. Next on, we have significance testing. That is, we use p values to determine whether each predictor significantly impacts the output. That is, a small value that is less than 0.05 indicates that the predictor is important. And lastly, we have odds ratio calculation. That is, by exponentiating the coefficient, we calculate the odds ratio with which quantifies with effect size. For example, an odds ratio of 1.5 means a 1 unit increase in one in a predictor raises the odds and the events by 50%. Now, accessing model fit, we have ROC curve, AUC score, confusion matrix, and GOF, that is goodness of fit, GFF, that is goodness of fit statistic. Now, ROC curve shows the trade off between the sensitivity, that is true positive rate, and specificity, that is true negative state, and it closer the curve is to top left corner and the better model. We have now AUC score, that is area under the curve, that ranges from 0 that ranges for from zero point 0.5 to one that is random guess to the perfect performance. And we have now confusion matrix that summarizes the classification results into true positive, true negative, false positive, and false negative. It's a handy tool to evaluate accuracy. And then we have goodness of fit statistics that evaluates how well the model fits the observed data. uh, Now is Poisson regression. Now let's switch to the gears to Poisson regression, which uses model to count data, things like number of purchase, number of accident, number of website reached. Now, about it, so key concepts of Poisson regression. Firstly, we have count data, that is, Poisson regression predicts the frequency of event occurring in a fixed period or space. For example, consider how many insurance claim will a customer file in a year, how many cars will pass through a toll booth every hour. Now, next on we have Poisson distribution. That is, this model assumes that the responsive variables follows a Poisson distribution where the mean equals to the variance. That is, it is ideal for modeling data with non-negative integer values. And then we have over dispersion. That is, sometimes when the variance exceeds the mean, violating the Poisson assumption, this is known as over dispersion and might require alternate methods like negative binomial regression. Now, let's look about the. One second, I'll just. Okay, so this is about the Poisson distribution and contingency variables, that is count data analysis, contingency table analysis, and over dispersion. So, count data analysis determines how the probability of an event changes with the variations in predictor variables. Next on, we have contingency table analysis that tests the data of the categorical variables, comparing the observed counts and expected counts. And then over discussion that occurs when the variance exceeds mean. And lastly, applications and interpolations of Poisson regression. So let's look at where Poisson regression shines. Firstly, we have insurance claim. That is, it predicts the number of claims fitted by policy holders. Next on traffic flow, that estimates the number of vehicles passing a specific highway point. And another is modeling customer purchases, that estimates or models how many items items a customer buys in a store. uh, so here is how we interpret Poisson regression. That is, coefficient represents the log of the of the expected count, and by exponentiating them, we get the rate ratio, which shows how expected count changes with the unit changes. And consider coefficient zero point 0.2 for advertising spend means advertising spend, meaning that one unit increases in advertising increases the expected speed count. uh, Now let's move to our coding part. So here about this code, I have imported necessary libraries such as pandas, numpy, stats model, sklearn and sub libraries, and scipy sets, which imports Poisson. Now, uh, creating synthetic data set from logistic regression, that is, we have created a random state and then random samples, and then try to fit in with our x, that is that will go into training and testing set, and then y with the which is our binary target. Now converting it to data frame, and then we are printing first five values of head. It is running. And yeah, I should probably run for the first one. Okay, the error is here, NP is not defined. We'll run this one and then we'll go to the next part. Okay, now let's run this. So we have gotten our first five models, and I think we can also suggest charts here. This is our data charts and with values, duty distribution and distribution. Now, next on logistic regression, how we are doing it, we are defining into data frame X logistic for features in X and target in Y, and then splitting the data, that is X train, X test, Y train, and test data split with the random state 42, and fitting the model, that is we initialize the model in a variable and then fitting the values and then Y predict. Now evaluation is here. Let's try to evaluate it. I think 1 second just. Let's try to run our model. So here is our classic confusion accuracy, that is 0.85, that is quite a good mark, and confusion matrix, that is okay, true false, true negative, false positive, false negative, and our classification report that tells what the precision recall F1 score and support was for 0 and 1. And I think it's a great output from logistic regression. Now let's move to our part of synthetic data set for Poisson regression. So here also we have randomly initiated a data. Now creating n samples, we have created 200 samples of it, and then features and the count of it, and then we are converting it into a data frame. Here you can see the data frame and also the statistical analysis of distribution, that is distribution, 2D distribution and its value. Now, how are we initiating Poisson regression? We are creating variables x and y, and then x will store the value like features, and y will store the count, and we have also adding a constant to the model, that is the intercept. Okay, this is X, and then fitting the model, and then printing the model summary, and then taking the predictions, and also calculating models such as mean and a predicted value. So here is our generalized linear model regression results, which have dependency variable, model family, link function, that is log, method, ILS, date, or today's date and time and iteration, and then observations are this much. We have already initiated that. Samples. These were samples, and then how many of residuals, how many models, scaled log likelihood, deviance, Pearson chi-square and pseudo chi-square, and also our mean actual count and mean predicted count. So that's a wrap for this video. We explored how the logistic regression predicts binary outcomes with probabilities, and how Poisson regression models the frequency of events in count data. If you found this video helpful, make sure to like, and thanks for watching this video.